what we had wrong statement, real, right? Mixed one or minus. So now
It's Hermitian, so it should have all real eigenvalues.
Yeah,
It's
who is that?
Hermitian, so it should have all real eigenvalues. I think it's Hermitian, so it should have all three eigenvalues. Real.
Yes, yeah,
It's
who is that?
Hermitian, so it should have
Right.
all real
So a
eigenvalues.
lot
I
of
think it's
people I think
Hermitian,
have
so it should
figured
have all
out.
three eigenvalues. Real.
Yes, yeah,
It's
who is that?
Hermitian, so
Fardeen
it
is
should
also
have
saying,
Right.
so
all
yes,
real
it's
eigenvalues.
an
I think it's
Hermitian
Hermitian,
matrix,
so
so
it
it
should have all three
ought to have.
eigenvalues.
Yes, yeah,
It's
who is that?
Hermitian, so
Fardeen
it
is
should
also
have
saying,
all
so yes,
real
it's
eigenvalues.
an
I think it's
Hermitian
Hermitian,
matrix,
so
so
it
it
should have all three
ought to have.
eigenvalues.
Yes, yeah, who is that?
Hermitian,
Fardeen is also
so
saying,
which
so
option is
yes,
correct?
it's an Hermitian. Everybody understood? Very simple logic is Hermitian matrix.
Yes, sir.
I think is correct.
It's Hermitian, so it should have all real eigenvalues.
Yeah, who is that?
I think it's Hermitian, so it should have all three eigenvalues. Real.
Yes. Right. So a lot of people I think have figured out. Fardeen is also saying, so yes, it's an Hermitian matrix, so it ought to have all three eigenvalues as real. So which option is correct? C option is correct. Everybody understood? Very simple logic is Hermitian matrix.
Yes, sir.
Okay. So how are you solving it? Are you calculating it? Eigenvalues? Yes, Harshitwa, you are right. Option B is correct. How did you calculate it? Again, you are going to get square. Okay. Calculate a square will turn out to this. This is the way. Or +1 or -1. You can guess that option B is correct because trace is 0. Yes, because trace is 0. So one way of looking at is this, that if you can figure out there's an orthogonal matrix, then this is the way. Or other way of doing it, I mean, understanding this solution is that this is a very specific kind of matrix. If you see, so it has all the elements as one uh, in the diagonal, which is not the principal diagonal, right? The other diagonal. So such a matrix, when you square of such a matrix, so you will get an identity matrix always. So if A is the, you can try it. If you multiply it, if you calculate A square, will turn out to be identity matrix of 4 cross 4. It will be always be the case. So it's 6 cross 6 or 7 cross 7 or 8 cross 8, whatever it is. If all the elements in the other diagonals are 1, if you square, you would always get it. Now you know the Cayley-Hamilton theorem that every um, square matrix satisfies own every square matrix satisfies characteristic equation, that is, I can replace A by lambda, that is eigenvalue. Lambda square is 1. It means lambda is equal to +-1. So eigenvalues will be +1 or -1, and then rest, you know, the trace is 0. So that's why option B is the correct option. Like, this is another way of looking at it. Okay. Yes.
Sir, which means A is an involutory matrix.
Uh, Involutory matrix, yes, you can say, because its square is identity.
But sir, is
This
it true that
is
for
it self-inverse? Yes. Yeah.
yes, sir. But is it true that for any involutory matrix, the eigenvalues would be +1 or -1?
Yes. Because whenever you have a square of any matrix as 1, there are only two choices for eigenvalue, +1 or -1.
Okay, sir.
Okay. Now the next one is a good question, non-trivial one. Satisfies own in the diagonal, which is not the principal diagonal, right? The other diagonal. So such a matrix, when you square of such a matrix, so you will get an identity matrix always. So if A is the, you can try it. If you multiply it, if you calculate A square, will turn out to be identity matrix of 4 cross 4. It will be always be the case. So it's 6 cross 6 or 7. Or 7 or 8. Yeah, next lecture. We will come in next more lecture. Simple tricks. Zeros of A, cosine of A. Okay. So for that, I will have to discuss diagonalization. It's a non-trivial process. So let's keep that discussion for a while aside till next lecture. What is the other way you can do it? I mean, you can do the problem. Can you think of anybody? Simple. I mean, not very difficult thing I'm asking.
Sir, we can convert into means expression of exponential, then connect it to some Taylor
Yes,
series.
yes,
Yes, sir.
try. Yes.
Okay, okay.
Yes, you can do that. Use the first principle, like it is exponential of A, right?
Yes, sir.
It is exponential of A. So it means, what's the, how to write the exponential of, let's say, anything, e to the power theta 1 plus theta
Means
by factorial 1,
one
theta
plus
square
yeah,
factorial 2, and so on and so forth.
yeah,
Exponential, how to expand it.
yeah.
Maclaurin series. So this will be a one in this case will be an identity because
Yes, sir.
A is A by factorial 1 means A is in matrix here.
Yes,
Similarly,
sir.
A square by factorial 2, A square is another matrix. A cube by factorial 3 is another matrix, like that. So this one is basically identity matrix here. And what is the dimension of A? 4 cross 4. So identity will also have a 4 cross 4 as its dimension. Fine.
Yes, sir.
Now our job is to find out these A square, A cube. A is given to us, so I can find out A square very quickly.
Yes, sir.
Try. Yes.
Okay, okay.
Yes, you can do that. Use the first principle, like it is exponential of A, right?
Yes, sir.
It is exponential of A. So it means, what's the, how to write the exponential of, let's say, anything, e to the power theta 1 plus theta
Means
by factorial 1,
one
theta
plus
square
yeah.
factorial 2 and so on and so forth, exponential how to expand it.
Yeah.
Maclaurin series. So this will be 1 in this case will be an identity because
Yes, sir.
a by factorial 1 means a is in matrix here. Similarly,
Yes,
a square by factorial 2, a square is another matrix. A cube by factorial 3 is another matrix, like that. So this 1 is basically identity matrix here. And what is the dimension of a 4 cross 4? So identity will also have a 4 cross 4 as its dimension. Fine.
Yes, sir.
Now our job is to find out these a square, a cube. A is given to us, so I can find out a square very quickly.
Yes, sir.
So in fact, I can write down a as, if you wish, pi by 4 outside. So I can write 0, 0, 1, 0, 0, minus 1, 0, 0, 1, 0, 0, minus 1, 0, 0, right? Like
It is
that.
coming identity, I guess. Means if you square it.
A square is coming identity.
Yeah, pi by 4 ka
Pi
square
square by
into
16 identity. Yes, yeah,
yeah,
that
yeah.
will. Pi square by 16 times identity.
Yes, sir.
That will come out. Okay. So if you want to check, other person can check at home. You just square it. Let's do it. I think I got some doubt. What is the exact value? Let me calculate it. A square will be pi square 16. I will get definitely, and then 0, 0, 0, 1, 0, 0, minus 1, 0, 0, 1, 0, 0, and minus 1, 0, 0, 0, and then again same matrix 0, 0, 0, 1, 0, 0, minus 1, 0, 0, 1, 0, 0, minus 1, 0, 0, 0. Now you see pi square by 16. So now you see it has a minus 1, it has 0. Here, right?
Oh, I made mistake. I think minus 1 be this outside will be pi square by
Yeah,
16.
that's
Minus will be
what
there.
that's
Yeah,
what I got as a doubt.
yes,
So
sir.
another one is 0, 0, 1, 0, and minus 1, yes, and 0 and 0, and then 0, minus 1, 0, and here we will get as minus 1, right? And 0, 0. So you will get basically minus
Yeah.
of
Yes.
pi square by 16 as identity, times identity. Fine. So you got a square as this, minus pi square 16 by times identity. Now what's my a cube? A cube is simply a square times a.
Yeah.
A
Both
square,
side is
yeah, a square is given as we have found out as pi square by 16 times identity, which means a itself, right?
yes, sir.
And a4 simply again a square, which is minus pi square by 16 times identity is square.
Yes, sir.
Like that. We can go on. So if we plug all this value in the exponential of a, right, which is the U matrix. So what is that? Identity 4 cross 4 plus a by factorial 1, a square, which is minus pi square by 16 times identity by factorial 2, right? Plus a cube by factorial 3. A cube is minus pi square by 16 times a. And what about a4? pi square by 16 pi to the power 4. Okay, let me write this thing this way. And identity, right?
Yes, sir.
And so on and so forth. And 4 factorial 4, of course, is there. And so on and so forth. Right? Okay. So let's do one thing. Identity I keep as it is, and I take common what? Pi square by 16. Okay. No, but a is there, no? So what should I do? A, have I missed anything? A cube is a square is pi square by identity. Fine. A cube is this, to the power of this. Yes. So what we can do here is we can combine few terms which are having, let's say,
Okay, yeah,
pi square.
cost
Otherwise,
term,
okay. Otherwise, we don't have to do anything, because what we have to calculate actually is the trace of this.
yes, sir.
So if I take the trace operation of this equation, so trace of u, because you remember I told you that the trace has the property that if you have matrix A and B, if you remember that, if you have the matrices, let's suppose A and B, the trace of A plus B is equal to trace of A
Plus trace of
plus
B.
trace of B. You remember this property which
Yeah,
I
it
told you?
can distribute, yeah.
So, yeah. So now if you take the trace operation of this, so which means trace of exponential of A is equal to trace of, first of all, trace of this, trace of identity of 4 cross 4, which is
4.
4, plus trace of A, this to trace of, first of all, trace of this, trace of identity of 4 cross 4, which is
Four.
4, plus trace of A, this trace of A, trace of A is, from the expression given matrix, you can find out trace of A is 0,
Yes, sir.
right? Trace of
Yeah.
A is 0. So this is 0. Fine. Now minus pi square by 16, 1 over 2 factorial. Identity, trace of identity is again 4.
Yes, sir.
And similarly 1 over uh, 3 factorial minus pi square by 16, and trace of A is again 0, and then pi square by 16 whole square, and trace of identity is again 4, like that. you keep on.
Yes, sir. We can
Now, yeah, if
combine
I
terms.
take, yeah, 4 and what you have to calculate trace, no? Asha, let's say I take 4 and what's common? Pi square by 16, huh? Okay, let's take 4 common first of all through the entire expression. So you get 1 minus pi square by 16 times factorial 2 plus 1 over factorial 3 minus pi square by 16, right? And what else? Square. Pi square by 16 square, 1 over factorial 4 times 4. So this one is 0, sorry. This one is 0. And the last one is pi square by 16 square, 1 over 4 factorial times 4, like that. Okay. So do you think any series is you can recognize out of it?
So cos theta series have 1 upon n factorial light type of thing, means
Yeah,
1
cos it.
minus.
Yeah,
Cos
1
3.
minus. Yes, 1 minus theta square by factorial 2 plus theta the power 4 by factorial 4, like that. I
Yes,
know.
sir. Hmm.
So if you see, okay, I made a small one mistake here. What is that? This 4 will not come here because I've taken 4 outside, yes, sir, for every term. So I will not have this 4, which I have not written. This is again 0, and this is 1 here, not 4. Okay, so this is 1 here. That's what I was thinking from where this 4 has come. Fine. Now it is completely cosine series. What's the expression? Cos of pi by 4, right? Cos theta.
Yes, sir.
Cos theta is equal to 1 minus theta square by factorial 2 plus theta to the power 4 by factorial 4, and so and so. so forth. So here theta is recognized as pi by 4, right? You see theta square is pi square by 16, theta to the power 4 by pi by 4 to the power 4. If you write it, it will become pi by 4 to the power 4 upon factor of 4 and so on and so forth. So it's like cosine series. So
Yes, sir.
4 cos pi by 4 is 1 by root 2 cos 45, which is 2 root 2
root. Yeah.
is pi square by 16, theta to the power 4 by pi by 4 to the power 4. If you write it, it will become pi by 4 to the power 4 upon factor of 4. And so on and so forth. So it's like cosine series. So
Yes, sir.
4 cos pi by 4 is 1 by root 2 cos 45, which is 2 root 2.
root. Yeah.
That's why option A. Got it?
Yes, sir.
Can you repeat who has written what? Can you repeat A square? I'm not getting it to identity. It's okay. So I think I've already done it. It is not identity. It is A square is minus pi square 16 times identity. diagonalization, which will multiply it, no? 0, 0. I'm not getting it to it's okay. So I think I've already done it. It is not identity. It is a square is minus pi square 16 times identity. Okay. You multiply it, no? 0, 0, 0, minus 1, again 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, again 0, 0, 0, minus 1, 3, okay, 0, 0, 0, 0, 0, 0, 0, 0, fine. 0, minus 1, 0, 0, fine. 0, 0, 1, 0, 0, 0, okay. 0, this one 0 minus 1, minus 1, and this last one is 0 and 0, 1, 0, 0, 0, 0, 0, 0, 0, and yeah, fine. It's fine. Soumya Priyadarshi is saying, got it now. Okay, fine. What else? Sir, can we solve using exponential of a is cosine a plus? Actually, this expression is when a is some iota theta kind of thing. Then exponential a is not cos a plus sine iota sine a. Exponential of iota a is as cos a plus iota sine a. Okay, Pardeen. And some a square now it's okay. All doubts are clear.
Yes, sir.
All doubts are clear, or should I repeat? Let me know if anyone wants me to repeat. Okay, I think sir. Okay, sir, my mistake. Okay, no problem. Soumya is saying yes, sir. Okay, who else? Darshan. Sir, how have you taken the theta value? Okay, see if you compare this expression, if you consider this pi by 4 to be theta, so this is nothing but theta square. This is theta to the power 4, right? Because I know this cos theta is this. So this, whenever I have 1 minus plus this kind of series, and I have factorial 2, factorial 4, and some squares and fours are coming, power 4 is coming. So this gives me this gives a doubt in my mind that it's a probably cosine series. So I will uh, cross check it. I will check it that whether it's satisfying this expression or not. So that if you compare this particular series and this series, so if you think theta is equal to pi by 4 in your head, so this will satisfy completely. That's how we can say that theta is pi by 4. Just by comparison. Okay, Darshini is saying got it. All right, so I think we should stop here because next thing I'm going to discuss the diagonalization, which will take some time, more than found out too straightforward. Means its eigenvalue will also satisfy the same equation, right? By Cayley Hamilton.
So first one.
First one. Who has answered it?
Abhyuday.
Acha. Why do you think the first one is correct?
So by Cayley-Hamilton theorem, we can
Fine. We can find out
replace
two of the eigenvalue. Yeah. So, but
two.
how did you decide the third one? Okay, so according to Cayley-Hamilton theorem, every matrix satisfies on characteristic equation. So it is saying the matrix M is satisfying this equation, which means its eigenvalue will also satisfy the same equation, right? By Cayley-Hamilton theorem. So therefore, if we factor it out, so M minus 2, yes, Soumya, 2 is the correct option. B is the correct option. Minus 3, M minus 2 equal to 0. So you get M equal to 2, 3. So two of the eigenvalues you come to know because the equation given was quadratic in nature, right? So we could have only found out two values, which we already did. But you see these two eigenvalues are there in three options, A, B, C. So which option is correct?
We'll put 1, 2, and 3, 1, 2, and 5, and check which follows.
Yes.
B follows.
So
Yeah.
yes. So you see the third eigenvalue, which is not possible to extract out from the given equation, but in the options, what are the what are the other values for given for third eigenvalue? And you see clearly that 2 and 3 are the for sure eigenvalues of the given matrix, but these two or three option values are only in A, B, C, three options. Now what we observe is that what is the third eigenvalue? According to the option 1, third eigenvalue should be 1. According to the option B, third eigenvalue should be 2. According to the option C, third eigenvalue should be 5. So whatever the eigenvalue is, will satisfy the characteristic equation. Will satisfy this equation because Cayley-Hamilton theorem says that every matrix satisfies on characteristic equation. That is, whatever equation is being satisfied by the matrix will also be satisfied by the eigenvalue, and vice versa. So you see, if we try M equal to 1, that doesn't satisfy this. M equal to 5 again will not satisfy it. M equal to 2, however, will satisfy it. So what we can guess from the given information at the best is that 2, 2, 3 is the right option. Directly to the of this thing, this solution. Now, there, since it is an n cross n given matrix, P is an n cross n matrix, which is given here, is an n cross n matrix. So it means it should have n eigenvalues, maybe distinct. Or maybe repetitive, but total n. Now it satisfy matrix satisfy p square is equal to p, which guarantees that its eigenvalues could be either 0 or 1. That is, the eigenvalues of p are either 0 or 1. So the second thing which is given in the question is the trace of p is n minus 1. That is, if you add all the eigenvalues, trace of a matrix is equal to the sum of the eigenvalues. If you add all the eigenvalues, you are going to get n minus 1. So if you have 1 and 0, 2 choices, then it's only one possibility is there, that n minus 1 eigenvalues are 1 and the rest one is 0, right? So it means out of n eigenvalues, n minus 1 are 1 and only one eigenvalue is 0, right? So therefore, okay, let me write down, since trace of p is n minus 1, it implies that only one of the eigenvalues is 0 and rest are 1, right? So therefore, if you in the question it is asked what's the determinant of P. The determinant of P is equal to the product of eigenvalues, right? And even if one of the matrix is equal, so the second thing which is given in the question is the trace of P is n minus 1. That is, if you add all the eigenvalues, trace of a matrix is equal to the sum of the eigenvalues. If you add all the eigenvalues, you are going to get n minus 1. So if you have 1 and 0, 2 choices, then it's only one possibility is there, that n minus 1 eigenvalues are 1 and the rest one is 0, right? So it means out of n eigenvalues, n minus 1 are 1 and only one eigenvalue is 0, right? So therefore, okay, let me write down, since trace of P is n minus 1, it implies that only one of the values is 0 and rest are 1. right? So therefore, if you in the question it is asked what's the determinant of P. The determinant of P is equal to the product of eigenvalues, right? And even if one of the eigenvalues is zero, as we already established that only one of the eigenvalues is zero, so the product will automatically turn out to be zero. Option B. All right. So it's just these are the simple application of what we wrote down as properties of different eigenvalues and properties of eigenvalues of different type of matrices, right? Got it? Okay, now okay. So now let's move to the diagonalization of a matrix. This is important. Now we will enter to the into the domain where you will get the NET and gate like questions, right? So diagonalization of a matrix, even TFR standard problem. Diagonalization of a matrix. How do you diagonalize a matrix, sir? Right? When do we say that a matrix is diagonalizable? All these things. Now, suppose if you have a matrix A, which is a square matrix of order n cross n, and suppose you find out its eigenvalues, which you have already discussed how to find out eigenvalues. So there are various possibilities. All these eigenvalues could be distinct. Or these eigenvalues could all be same, or some of them could be same and rest may be different, like that. All these possibilities are there. Okay. Now let's consider the possibility where all the eigenvalues are distinct, because at the most we can have n distinct eigenvalues, right? This is the maximum number of distinct eigenvalues we can have for a square matrix of order n cross n. Okay. So let's suppose there are n distinct eigenvalues. Now corresponding to these n distinct eigenvalues, namely lambda 1, lambda 2, lambda 3, lambda n, we can find out n normalized eigenvectors, right? I can find out n number of eigenvectors corresponding to each eigenvalues may happen, but let's suppose we have n normalized eigenvectors in our hand corresponding to lambda 1, lambda 2, lambda 3, lambda 3 respectively. Got it? Now out of those eigenvectors, if we construct a matrix, right, which we are calling as P. So now if we apply the operation P inverse AP, then it will diagonalize the matrix. So this is called the diagonalization of matrix. So I'm going to write down everything, you will understand. So what I'm saying is, if we have okay, and let's suppose it has n distinct eigenvalues. As lambda 1, lambda 2, all the way up to lambda n, right? And further, corresponding to lambda 1, lambda 2, lambda 3, lambda n, we have n eigenvectors. You can say normalized eigenvectors.